So, we have been talking about optics using ray approximations. That is, we're kind of ignoring the fact that light is a wave. And we're just picturing it as something that might look a little bit like a laser, like sort of a ray of light, or one beam of light propagating around, bouncing off things, bending as it enters new media. We can't ignore the wave nature of light forever, because light is a wave, and the fact is that waves do things that other constructions don't, and we've got to take that into account. One of the most important things that waves do is interfere with each other. And to say that word, it doesn't necessarily mean a pejorative thing like in everyday usage. Like if you interfere with something I'm doing, right, that's probably a bad thing. That's not necessarily what we mean here. This is all wrapped up in what we can call the concept of superposition. Waves superpose. The idea of superposition that if two waves, or more of course, of the same type, what I mean by that is two sound waves, or two light waves, or two electromagnetic waves, or whatever, of the same type, propagate through the same medium at the same time, the waves add together at every point. We say they superpose. Or you can say they exist in a state of superposition. What does that mean, they add together at every point? Well, the easiest thing to think of is when we think about mechanical waves, right? That's basically every type of wave except for light, as far as we're concerned here. The fact is that two people shouting is louder than one person shouting, right? What that means is that those waves are adding together. And if you're talking about the actual medium, like remember mechanical waves, like sound waves, need a medium to propagate. Right? So right now I'm saying things, and the air molecules and the space between my voice box and your eardrum are oscillating back and forth. If two of us were up here talking, they would just be oscillating with a greater amplitude. Right? Amplitude is related to volume for sound waves. So that's what I mean. In mechanical waves, the displacements of the media add together at every point. Electromagnetic waves, they don't displace the medium. They don't need a medium to propagate, even though they propagate through a medium. But what we would say for electromagnetic waves is the components of the fields add together, right? The electric fields would add together, the magnetic fields would add together at every point in just the normal rules of vector addition that you know. So I've given you some examples of what can happen. And these are really pristine, nice, pretty examples. Like the real world doesn't exist like that, right? So we'll talk about that as we get on. This is where we start. So for the first example over here, I've given you an example of two waves, and we'll assume that they're propagating to the same medium at the same time. Now, what I have matched up with these waves are their wavelength and frequency, right? Again, not normal, but this is the pristine example. So that is to say, they're at a maximum at the same time, they're at a minimum at the same time, their wavelengths and frequencies are matched. We say that they are in phase, and that's an important phrase. I'll write it down. Example 1 here, these are in phase. What that means is what I said. Frequencies and wavelengths are matched up. So, if this is a mechanical wave, the amplitude here would represent the displacement of the medium. If it's an electromagnetic wave, the amplitude here would represent the maximum E field or B field. It doesn't matter which one we talk about. We can just say that we have this wave which has an amplitude, we'll say an A1, and this wave has a different amplitude, A2. And what I'm saying now is that out of these waves, there will come a resultant wave. Let me draw it here again. Everybody have the definition of superposition so I can erase it? Out of these two waves will come a resultant wave, which, if I can match it up, will look something like this. Right? It's terrible art, but you see what's going on, right? Where the amplitude of this one is A1 plus A2. They're going to add together at every point. So they're superposing. Out of that superposition comes this concept, which we call interference. Right? The interference is the actual adding together of their amplitudes. In this particular case, because the amplitude of the resultant wave is bigger than the amplitude of either of the constituent waves, we would call this constructive interference. Constructive interference. And again, this is why two people shouting is louder than one person shouting. Okay, next to it, I have waves which I've still matched up the frequency and wavelength, but these are not in phase because you notice that where there's a peak in one, there's a trough in the other one. So we would say that these waves are completely out of phase, or you can sometimes say 180 degrees out of phase. So that's a little bit of a misnomer, that's what people say. I'm happy with out of phase. So what happens here? You can think of a mechanical medium. If this is a mechanical wave, this one is trying to push the medium in one direction, a certain distance. This one is trying to push it in the opposite direction, a certain distance. Right? And so you're going to get some sort of cancellation. It looks to me like this one has a larger amplitude than this one. We'll call this A1 again. We'll call this A2. The resultant wave would look like this, or something like this. Right. Where the amplitude of this wave it would be the magnitude of the difference between them, right? Positive and negatives don't matter for amplitude; it's always positive. I'm just going to write A2 minus A1. Because A2, as I've drawn it, is bigger, but A1 minus A2 works just as well as long as you just remember to take the amplitude, which I have, the absolute value. I just keep saying amplitude. Modulus is what I'm looking for. Take the modulus, or the absolute value of the difference of these two amplitudes, just to make it positive. We would call this destructive interference, for obvious reasons. Right? The amplitude of the resultant wave is less than the amplitude of any of the resultant waves. I used to struggle with finding real-world examples of this. My background is in music. I worked in the music industry. I've run sound and installed sound systems and traveled for a long time before I went to school for physics. And this is something we dealt with in the sound industry a lot. These days, we don't really get that a whole lot. But if you've ever worked with like stereo systems, or maybe hooking up a car stereo, this is what happens when you accidentally wire one of your speakers backwards, right? What you got?
That's how sound distortion works too.
Sound what?
Sound distortion.
It depends on what you mean by distortion. Probably not, but I'll hold on to your question until I'm finished, and then you can ask it again. Because I'm not sure. See where I'm going with it. See if that answers your question. Okay. But like if you wire one of your speakers backwards, one of your speakers fires forwards as the other one fires backwards, and you create this weird effect. If you've ever been walking around a club when they're playing music and you hit a particular spot where the sound just goes all crazy, like just kind of can't tell where you are, it sounds funky, probably one of their speakers internally to the cabinet is wired backwards, because you get this weird effect. But I say that, even, it looks on most of your faces like I don't have any idea what you're talking about. But about 5 years ago, a real-world example started getting really, really popular because most everybody in here has some sort of experience with noise-canceling headphones, right? This is how they do it. There's always sound that gets into your ears around the cups, right? There's always ambient noise. So noise-canceling headphones have an external microphone that picks up that ambient noise and inverts the phase. They make the peaks into troughs and the troughs into peaks. And so you get sound coming into your ears just naturally around your cups, which is in one phase. And then internally to your speaker system, they pick up that sound and invert the phase and then mix that in with your music. And so when the inverted sound mixes in with the outside sound, it just goes away. And you can get pretty good with it if you have really nice sound noise. No noise-canceling headphones are perfect because it's a little hard to do because real-world sounds are very complex. They're not like these nice, pretty sine waves I've given you, right? Real-world sounds are very complex. And so it's a little difficult to do, but the technology is advanced to where they get really, really, really nice and stuff. Now, what do you mean by distortion?
Like sound distortion. Like a distortion of the sound wave itself.
So like when it sounds like all fuzzy and stuff?
Yeah.
No, that's not this. That is going to have something to do, it depends. So you can do it electronically, just by overloading the amplifier. You push it past its limits, which is basically every rock song you've ever heard. Distorted guitars are basically just driving transistors, well, these days transistors, back in the old day vacuum tubes, driving them past their design specs, and they create that fuzzy sound. Sometimes it's done with a circuit, it's by overloading a circuit in creative ways. Sometimes the distortion you hear is because you're overloading your speakers, like you're making them fire farther than they want to go. So there's multiple ways distortion can occur. This is not strictly speaking distortion, though. That's normally an electronic phenomenon. This is just a wave phenomenon. But yeah, it is how noise canceling speakers work. So you get destructive interference here. And there's, of course, it can be combined in interesting ways, and I'll show you something about that in a second. But what I want to point out to you here is that if you look at the waves that I have drawn here, what would you expect here? Constructive interference or destructive interference? Destructive interference, right? I'm matching up peaks to troughs. So if these two waves are propagating through a medium, this maximum lines up with this minimum, and things just go away, right? But the difference here is not that the waves were out of phase at their source, right? Let's assume that these origin points are the source of the wave, either a speaker or a light bulb or my voice box, whatever you want to think about. The source of the wave is located at the origin here. In these two examples, they're in phase or out of phase because they're in phase or out of phase at the source. In other words, this one is producing a peak when that one produces a peak. This one's producing a trough at the same time that's producing a peak. But these are not out of phase at their source, right? Both of these sources are producing a peak. What has made them out of phase? I have moved one of them, right? I've taken this guy and I've moved it back. How far did I move it in terms of wave parameters? You're thinking of mathematical parameters, and I appreciate that. But in terms of wave parameters, right? What have I marked out on there? It's the wavelength, right? How far back did I move this in terms of the wavelength? Half of the wavelength, right? That's interesting. So I take this system, which is in phase and producing constructive interference, and I just grab one of my sound sources or wave sources, and I move it back a physical distance equal to half of the wavelength that it's producing, and all of a sudden I get destructive interference. What I have done is I've made a path length difference. What does that mean? Well, the path that this wave takes from the source to the detector, whether that's a light bulb to your eyes, or a speaker to your ears, or whatever, some sort of detector in a lab, it doesn't really matter. Anything that can pick up this wave. The difference between these two waves is the length that the path that they take to get from the source to the detector. And a half integer multiple, right? Let me say that again. A half integer multiple of a wavelength will get you destructive interference. Full integer multiples of the wavelength will get you constructive interference. This is what I mean. The path length difference between these two is exactly 0, right? That's an integer multiple of the wavelength. 0 is an integer. It's kind of a weird one, but it's an integer, right? This, pull it back half a wavelength. I've got a 1/2 lambda path length difference. That's a half integer multiple of the wavelength. What would happen if I displaced this backwards another half of a wavelength? Well, then, instead of this peak and this trough being lined up, this peak and this peak would be lined up, right? My path length difference then would be 1 lambda, and I would get constructive interference. And then if I move it back another half of a wavelength, I'm lining this guy up with this trough. That's 3/2 of a wavelength that I've moved it back. That's a half integer multiple. So you see the pattern here. Integer multiples get me constructive interference. That's 0 lambda, 1 lambda, 2 lambda, 3 lambda. Half integer multiples get me destructive. That's lambda over 2, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, etc. What makes the difference here is the path length, whether or not I get constructive or destructive interference. Okay, does that make some sense? Okay. Of course, like I said, in the real world, not everything's so pretty. So let me give you try to give you another example. Because this is interesting. We're going to use sound as an example because it's something that we all understand, or at least we know about it. Normal sound sources do not just produce sine waves. Have you ever heard an actual sine wave? It's very sterile, right? Normal sound sources have all sorts of richness to them. And that is because normal sound sources are made up not of just one kind of wave, but of lots of different kinds of waves. To see what I mean, let's say that I have 2 waves propagating in the same medium that do not have the same wavelength or frequency. Right. All right, so my task now is to come up with something that looks like the resultant wave of this. And so let me divide this into some regions, right? I'm using the 0 points of these waves to divide them up, right? Because there's going to be all sorts of crazy stuff going over here. In this region here, what sort of interference do I have? Constructive or destructive? I've got constructive here. What about here? Destructive, but be careful here. That doesn't necessarily mean the resultant wave will disappear because these have different amplitudes. It doesn't even mean the resultant wave will be negative because this looks like it's still going to win, right? So I get destructive interference in the sense that the amplitude of the resultant is less than either one of these, but it looks like the wave is still going to be positive. But these functions are also changing at different rates, and so my wave is not going to be pretty, right? It's going to be kind of funky. Here I get constructive, and here I get destructive, and here, what do I get here? Constructive, that's right. The resultant wave of the amplitude of the resultant is going to be bigger than either one of these. Don't let the fact that these are both negative fool you. They're in the same direction. That's constructive interference. Right? Constructive. Here is destructive. Here is constructive. Here is destructive. And that's all I got. So, this is going to be a nightmare, but I'll give it a heck. Right? Let me get a different color. And well, actually, I'll do it a different color. I'll try to do it on this. Right? So, let's try to superimpose this. Not superpose, that's what waves do. Superimpose, that's what I'm doing the job. Alright, so it looks like I'm going to get a nice tall wave here, but then it kind of rolls over and maybe comes down a little bit. But then I've got constructive, and so that goes up, and then destructive. But now it drops down sharply because this one is winning. And then constructive again, so it kind of levels off. And then destructive, and then constructive, and then destructive, and then we're going to kind of go up there. So I get this waveform, which is not a simple sine wave, right? So you can imagine if I were to add another wave in here, it would get even more complicated. But you can also imagine that if I were to take two waves and find out the resultant, and then I would take two different waves and combine them, that resultant would look much different than this resultant. Right? If we're talking about sound, this is what we call the timbre of a sound. It's the characteristic way something sounds. It's why you can tell the difference between your girlfriend or boyfriend's voice and your mother or father's voice, right? I hope you can tell the difference. That would be awkward kidding, right? Our voices sound different. It's why a trumpet sounds different than a guitar. It's why an alarm bell, to tell you to get out of the building because it's a fire alarm, sounds different than a soothing piece of music that's going to put you to sleep, right? The timbre of the sound. And that goes because of this constructive, destructive interference that occurs all over the place. This is also this is more biology than physics, but I think it's fascinating. To take the pink waves and put them together to form the blue wave is not a big deal, right? I did it badly here on the board. You can do it with a simple spreadsheet just by adding stuff together. So going that way is actually really simple. Going the other way is actually incredibly hard. If I just gave you the blue wave, said, hey, come up with the pink wave. Whoa. You can't do it just by drawing it on the board. You have to use a mathematical technique called a Fourier transform to do it. So putting them together is easy. Taking them apart is really hard. Here's what I think is fascinating. Your ear can do that just naturally. Because if I were to be sitting up here talking to you, and your girlfriend or boyfriend were to be sitting up here talking to you at the same time, you might not be able to understand all the words we're saying, but you could absolutely tell the difference between her voice, or his voice, and my voice, right? It wouldn't be a big deal for you to differentiate that. What your ear is naturally doing is taking the blue and differentiating it into the pinks. Like, your ear does that just normally. And actually, the way it does it is really fascinating. I don't have time to get into it.